Are you ready, Georg? Ready? Okay. So I'll let you know 5 minutes before. We're happy to see your research talk now, and let's start the afternoon session of the last day. Go ahead, Georg.
Thank you. Yeah, after I spent now 3 talks about low-dimensional supersymmetric gauge theories, I now want to switch again back to, switch to 4 dimensions, which have already been mentioned in David's talk and discussed in more detail. I think this is a good thing to compare this and also to explain a little bit more the difficulties, the additional difficulties that you have with simulations of QCD-like theories in higher dimensions, and also what kind of problems you face if you are investigating theories that are not exactly like QCD. Because for QCD, there's a lot of experience in the literature. A lot of collaborations have investigated QCD on the lattice. So you know the parameter region, you know how to simulate this with good algorithms, etc. So therefore, one has to keep in mind that this kind of previous knowledge does not exist for if you study slightly different theories. The results will not be the newest ones that we have for these. That's mainly because the new developments are rather technical concerning the randomization of the supercurrent, which is a little bit complicated in this if you go to the lattice. But this is too technical to discuss it here in this kind of talks. I will discuss basically fermions, gauge theories with fermions in the adjoint representation, and supersymmetric n equals 1 supersymmetric Young-Mills theory is one example. It has 1 Majorana fermion in the adjoint representation, and the one flavor model that I will discuss in the end has 1 Dirac fermion, so to say the twice the number of fermion fields in the adjoint representation. These have some connections to theories beyond the standard model, of course, supersymmetric extensions of the standard model, where you have these have been considered in walking technicolor scenarios, etc. And they also have some application if you go to some analytic consideration about an adiabatic continuity that was, I think, mentioned in part of Mithat's talks. And the main question is, I will discuss about this one Majorana, which is half a Dirac flavor, so to say. And there, the main concern is to have supersymmetry intact on the lattice. Then there is a lot of simulation have been done for this 2-flavor adjoint theory. And what is not so clear is the theory in between, where you have 1 Dirac flavor. One has to note that the chiral symmetry breaking pattern, due to the fact that you have fermions in the adjoint representation, is slightly different. But yeah, I will come to that in the discussion then in the later discussions of the theory. So this is supersymmetric Young-Mills theory. It just looks like QCD. The difference is that the fermions are now in the adjoint representation and not in the fundamental representation as in QCD, and that these are Majorana fermions and no Dirac fermions. As I said, the main motivations are extensions of the standard, and then these theoretical considerations and also some additional considerations of the theory in what is called orientifold planar equivalence. And the last part is, of course, if you want to go to theories with more, with extended supersymmetry or supersymmetric QCD, you always need this sector as a gauge sector. So it corresponds basically to the part of quenched super QCD that we are here investigating. So with infinitely heavy matter fields attached to supersymmetric QCD. The symmetries of the theory are if you don't have a mass term for this fermions that I've added here, then you have supersymmetry. This mass term will lead to a soft supersymmetry breaking. Then you have a chiral symmetry, which in contrast to QCD, where it gets completely broken by the anomaly, is broken only to a discrete subgroup. And this discrete subgroup then gets spontaneously broken by the appearance of a gluino condensate in these theories. Now we can discretize the theory in the most straightforward way that you have learned so the standard way that you learned in Anna's lectures, so with the usual plaquette action and then a Wilson term. And the problem here is that, as I said in my lectures, that supersymmetry gets always broken on the lattice. But in addition, also, of course, since you add the Wilson term, chiral symmetry gets broken. Now, you would have to restore these symmetries in the continuum limit, and therefore you would have to add possible counter terms and fine-tune their signals. The good thing is that actually, which has been analyzed by considering the relevance of all these counter terms, is that if you have chiral symmetry, if you are able to tune towards the chiral limit in the model, then supersymmetry comes basically as an accidental symmetry. This is what I told you about these different realizations of the symmetry on the lattice. So it can be that you have enough symmetry that it suppresses all kind of possible terms that you would have to tune well enough that you get the complete supersymmetry just when you go to the continuum limit. And this is the case in the case of n=1 supersymmetric Yang-Mills theory, as long as you have chiral symmetry on the lattice. If you don't have chiral symmetry, then you can tune one parameter, which is the mass parameter in this theory, to 0, and then you will have the correct supersymmetric limit. The disadvantage is in these higher dimensional theories, in contrast to this 1 and 2 dimensions, where you can, due to supernormalizability, you can compute what kind of tuning you have to do. Here you have to determine it non-perturbatively. So you need some kind of word identities or some kind of symmetry arguments that tell you this is the parameter that you have to set in your Lagrangian, in your simulations, in order to have to tune towards the supersymmetric, towards the limit where the symmetry is restored. This tuning is, for chiral symmetry, this tuning can be avoided if you use a realization in what I told you about this Ginzburg-Wilson relation, which is a relation derived due to randomization group arguments. And this leads to a guaranteed recovery of this chiral symmetry in the continuum. And if you are able to use this, then you automatically get, as an accidental additional symmetry, supersymmetry in the continuum limit. Now, what can you check in this theory? This theory has confinement, confines at low energies, and therefore at low energies you observe only a particle spectrum of bound states. And these can be either states that look like mesons in QCD, or it can be glue balls, or something additional that you only have with fermions in the joint representation. You can generate some fermionic operators from the combination of the with the gauge fields. And you can then construct multiplets, and it's of course plausible that you have the simplest possible supersymmetry multiplet, a chiral multiplet, which builds up basically the multiplet of the lattice states in this theory. And we have considered basically these operators on the lattice that correspond to these bound states and measured them. It turns out that this is really practically complicated. This is an additional problem in higher dimensions in the theories. You have to apply a lot of techniques to get enough signal for your final measurements. And I will just report here on some final measurements that appeared already in 2019 about SU3 superimmense theory. In addition, the theory, due to the appearance of this Majorana fermions that generate a Pfaffian like in this lower dimensional theories, you have to worry about the sign problem. The good thing is that in this theory, it's really a lattice artifact, and you get a positive sign in the continuum limit, but you have to monitor it on the lattice, and this is done here by monitoring the eigenvalues. This is also something that you cannot do for other theories because they have a more complicated dependence of the Pfaffian on this or a more complicated eigenvalue structure, but here it's enough to calculate a subset of the eigenvalues and determine the Pfaffian sign from this subset of eigenvalues. Then you measure all of these states, and you do then, since you cannot simulate exactly at the point where the fermion mass vanishes, you have to extrapolate in the fermion mass, and this determines your tuning to the chiral limit. And then at this chiral limit, you obtain the particle masses that should form a multiplet. And you see that if you are at a rather coarse lattice spacing, in higher dimensions, always you cannot use just the coupling constant to express everything in dimensionless quantities. You have to input another measurement to fix the units basically of your measurements. And this determines at a particular value of the gauge coupling then your lattice spacing. And at a rather coarse lattice spacing, you see that there's a rather large gap in the spectrum, and then you go to larger beta, which means smaller lattice spacings, and then you observe that somehow a multiplet forms. You can do this then more precise, make a combination of different fits, and then you see that, in fact, you get supersymmetry restored in the continuum limit. So this is, it's kind of expected from the arguments that you have about the restoration of supersymmetry if you have chiral symmetry on the lattice. But it's also good to have it verified, because you never know how difficult it is to approach this regime. And it seems really that this is feasible in the four-dimensional lattice simulations. You can then also do some checks of supersymmetric word identities that also support the restoration in this chiral and then continuum limit. Now, some other non-perturbative things that you can investigate are the phases of these theories. In QCD, you look at this phase diagram where you have one corner which corresponds to the pure gauge theory, where you have the confinement-deconfinement transition. Then at low fermion masses, you have a transition that comes from the chiral symmetry. And the physical point where you want to simulate usually lies in this crossover region. So this is different if you look at super Yang-Mills theory, because in this case you have fermions on the lattice that respect the center symmetry that is broken at the deconfinement transition. And this means you can have two separate transitions. One is signaled by the breaking of center symmetry, and one is signaled by the breaking of chiral symmetry. And these can be independent, or it can be at the same point. And you have different order parameters, the Polyakov loop and then the chiral condensate that determine these phase transitions. In different lattice investigations with actually another fermion content that we are considering here, there have been found some. So first of all, there are theoretical bounds from 't Hooft anomaly matching that this chiral transition temperature should be above this deconfinement transition. But what has been found in lattice and in some lattice investigation of other theories, which also consider adjoint fermions, is that there is rather large difference that is expected for the chiral and deconfinement transition. But in these investigations, probably the systematics is most likely not really under control. What we have found is that within our precision, these two transitions coincide. You see here peaks of the susceptibility, which signal the point of the transition. And therefore, we deduce that this is a signal that you have here really somehow a relation between deconfinement and chiral transition. There are even some arguments in string theory that you find also in these papers that there should be such a coincidence of the two transitions. And these are not exact arguments, but looks like there are also some theoretical argument that that there should be a relation, at least for the super Yang-Mills case. Then the other interesting things about phase transitions is you can just change the boundary conditions for the fermions, which are antiperiodic in the temporal boundary, if you want to measure finite temperature. If you have periodic boundary conditions, what you are actually measuring is a twisted partition function that is called the Witten index. And this gives you an additional measure whether supersymmetry is realized in the theory or not, because it's a sum. It's basically a thermal sum where you have the contributions from fermions and bosons all with opposite signs. And if you have a cancellation of these, then of course you have supersymmetry, and therefore, if this Witten index doesn't depend on the temperature, then this is an indication. So it's a derivative of the Witten index, which basically gives you the difference between all of the bosonic and fermionic energy levels. If this vanishes, then you know that you have supersymmetry realized in a good way in these theories. This is also related, of course, to Iguchi-Kawai reductions with adjoint fermions, where you use a similar mechanism to shrink the volume without having to wonder about possible phase transitions that are in the way. And we have done the investigation. This is a little bit complicated to see here. So the thermal transition, which is a deconfinement transition for antiperiodic boundary conditions, and this shows you that the Polyakov loop rises for different fermion masses that we have investigated here. If we switch to periodic boundary conditions, then you see that you get only this kind of signal here. Actually, this is a signal for 3 phases if you are at larger fermion masses. One confined, one deconfined, and then one reconfined phase that appears in these theories. But the important thing is that this intermediate phase, this is shown here, it gets smaller and vanishes if you go to larger kappa, which means smaller fermion masses. So it eventually, in the supersymmetric limit, you get here just a flat line, so you don't see any phase transition anymore. So this is an indication for the fact that you have intact supersymmetry in the simulation in this chiral limit. Of course, there's no continuum limit here, so there's some remnant effect, but it's at least a good indication that you are quite close to the continuum limit. Okay, we have done some further investigations of this. I just jump over this. And the next step that we have investigated were overlap fermions. I told you that basically chiral symmetry can be realized in terms of the Ginzburg-Wilson relation. And one way to realize this Ginzburg-Wilson relation is in terms of these overlap fermions. These have a rather more involved structure than the Dirac-Wilson kernel that only involves nearest neighbor, and can be written, in fact, in terms of a form where you have here the gamma 5 times the Dirac-Wilson operator, and then you have to apply a sign function to this matrix. This sign function can be written like this, because this is a Hermitian matrix, and then you can approximate the square root that you have here in terms of a rational or a polynomial approximation. And you can then go to, we have done this in a polynomial way, and went up to a certain order, and then try to extrapolate the results to the limit of infinite n, so arbitrary, so large orders of the polynomial, to get to the final results for this simulation with overlap fermions. This relation, if you look at the eigenvalue spectrum of the overlap operator, it implies that the eigenvalues should lie on a circle. And this is what's shown here. So you have for better and better approximations, polynomial approximations, the circle is better and better approximated. And this shows the chiral symmetry realization here on the lattice. We did then, we measured the Gluino condensate then with these overlap fermions and extrapolated them to the large n limit. And actually, what is quite remarkable, we found some good agreement with previous results done with another type of Ginzburg-Wilson fermions, which are domain wall fermions, and also results that have been obtained with an independent way to measure the condensate, because with Wilson fermions, you get always some randomization of this condensate. And we have done this with gradient flow randomization, and they seem to be agree quite nicely. Now, as a last part, I will discuss a little bit what happens if you go away from this supersymmetric Yang-Mills theory, consider theories with a larger number of fermions. The interesting thing is that this brings you in a range where you can observe a completely different infrared scenario of the theory. So, and you know, if you go to very large number of fermion flavors, then in a QCD-like theory, you lose asymptotic freedom that you can even see if you just look at the perturbative beta function. Now, in between the QCD-like and the regime where you lose asymptotic freedom, there's an intermediate range where the running of the coupling, so the beta function, goes to 0, so an intermediate range of the number of flavors, and you have an infrared fixed point. This is called the conformal window which has a strong dynamics which is quite different from QCD, where all masses basically scale to 0 if you set the mass parameter in the theory to 0. So then you lose any kind of scale in the theory, and all masses should scale to 0. there have been a lot of investigations concerning the theory with two adjoint Dirac flavors, and these investigations all seem to indicate that you are with the two-flavor theory in this scenario. What is quite remarkable in these theories is that you get always a scalar that is even lighter than the particles that you would assume to be if you have chirosymmetry breaking the pseudonumber Goldstone bosons. And yeah, and you can then also determine the mass anomalous dimension, which is actually quite small in these theories, which is a little bit disfavored if you are looking for some kind of X scenarios. Now, the big question is what happens if you go just to one Dirac flavor, and there have actually been very different scenarios being suggested for this theory. There's a QCD-like and chirosymmetry breaking scenario that has been proposed. It could also be that the conformal window in the non-perturbative regime really extends towards even this one flavor theory. And then it could be that you have even another scenario which is not excluded by Clifton-Normally matching, so it has been brought forward in this publication, which is that you have a light baryonic state in the infrared.
5 minutes.
Yeah, okay. And therefore, and of course, it would also be interesting to investigate whether you get a larger mass anomalous dimension, which has been the original motivation to consider the theory, than in the two-flavor case. Yeah, and these, unfortunately, the lattice investigations for this theory are so far not completely conclusive. That very small dependence only on the fermion mass of the states, if you express them in some, if you express them with some scale that you also determine from the theory, then of course these should be rather constant because everything should scale with in the same way to zero in this conformal limit if you turn the mass to zero. Therefore, you expect constant ratios. This is not really completely observed here, and but on the other hand, for example, you get a very light scalar glue ball here, which is also not completely expected if you have a chirosymmetry breaking scenario. So currently, this is not really settled out. So we have therefore also applied so these are studies always done with Wilson fermions, and we have therefore also tried our overlap implementation. Here's just a measurement of the violation of the Ginzburg-Wilson relation, how it turns to zero if you go to larger, better and better polynomial approximations. And we have investigated this on quite small lattices and extrapolated then this large, this in the polynomial approximation to get to the chiral limit. So what we observed is that we can do this with a chiral condensate for different discretization, for different lattice spacings. And the chiral condensate extrapolated in these large limit gives in our simulations a finite value. So this would indicate that in this overlap studies rather favors here chirosymmetry breaking scenario. Okay, so I just conclude with just some general remarks. So this series with fermion in the joint representation provide a nice and interesting field to test theoretical predictions or some theoretical developments and also extensions of the standard model, I've shown that n=1 supersymmetric Yang-Mills theory is actually quite well under control with respect to restoration of supersymmetry in the continuum limit. There are still technical difficulties if you want to get really precise results. You have to invest really quite some computing power and time. And then there's also, I taught you about this, this question whether if you get to a larger number of fermions that you actually go into some kind of conformal scenario, which is not completely understood for the one flavor case. For the two flavor, it's rather expected to be in the conformal window. And I've also shown that these first studies with overlap fermions on rather coarse lattices so far.
Okay, thank you. Let's take care. Any questions?
Yeah, I haven't had experience even indirectly with using overlap, but this N is huge. Isn't this very expensive?
It is expensive.
I mean, this is, you know, only by comparison, but in the US, almost everybody thinks domain wall is more efficient to get the same answer. Now, there's another issue, but maybe it doesn't come up here. The thing that they worry about in QCD is that when you get the thing too chiral, you inhibit tunneling of the instantons.
Yeah,
now, is that a problem here as well?
I mean, this is basically the fact why we choose another. So there are several reasons why we choose this polynomial approximation. that we want to avoid this tunneling problem because it leads to zero modes that you cannot really approximate with any kind of rational approximation. And then
sorry, you don't want to inhibit tunneling, right? You want tunneling.
Yes.
Yes. Okay.
So we don't want to simulate with fixed topology.
Right. Exactly. Yeah.
Yeah, and this is why if you do a polynomial approximation, you smoothen out this transition between the topological sectors.
Yeah, but all that means is that a very small domain wall would have done as well. The domain wall just gives you the same step function. It's just a means to the same thing. And domain wall, particularly if you do the Mobius version, when L is 10 or 12, it's fine. And in fact, if you go farther, you're going to have this game between tunneling and not tunneling. So I would think it'd be immensely more efficient to use domain wall.
We started actually already to look We started already to look into the domain wall. The thing is, of course, they also don't come for free. On these small lattices and for the first investigation, we just wanted to see whether we get a reasonable signal, and therefore our overlap was fine. But you're, of course, right. If we now want to move on to go to larger lattices, we should consider and compare with other things, and this is what we are doing.
I think it's a big win to go to domain wall.
Yeah, we are actually, so some collaborator is looking at the grid code.
Yeah, right. There's very finely tuned stuff. There's all kinds of stuff. I assume most of the QCD tuning will go over to this, and it will be much more efficient, I think.
Yeah.
Okay.
Yeah, there's still a considerable cost factor in them.
Well, of course, but you're paying the same cost factor. Every time you do a polynomial, you're just equivalent to making more slices.
Yeah.
So it's exactly the same issue, except for domain wall is more efficient.
Okay.
David?
By the way, just to say it, Tony Kennedy showed that all kinds of approximations of the step function can be turned into domain wall algorithms.
Yeah,
so there's a one-to-one correspondence, okay?
I discussed already with him at the Lattice conference, and he, I know this kind of approximation.
So this one is working.
You can use this one.
Sorry to run back and forth. I got a bit confused in my mind with your discussion about the derivative of the Witten index in the analytic continuity study.
Yeah.
So that's the derivative with respect to temperature.
Yes.
And this is a setup with periodic boundary conditions in all directions for all the fields. Is the temperature well defined in that lattice setup?
You have to. It's not the temperature actually. It's then the radius of a compactified direction that you.
Okay.
So it's
I'm
not,
happy
it's not
with
the
that.
temperature, but you get the same, except for the different boundary condition. You can always rephrase it in something where you have the energies and then beta, this beta Boltzmann time the energy. And since you have then the contribution with opposite sign, the differentiation with respect to beta brings down the energies, and then you have the energy differences.
I think that satisfies my initial confusion. Thank you.
I have one last question. Did you look at the spectrum of the 0++ and the other multiplet to see if they would also degenerate?
You mean the mixing?
Well, there's usually two types of glue balls, right? There's the glue ball, the globalino, and then they have different numbers. Do they all have the same mass, or?
So the thing is, on the lattice you get a mixing between this. So in a really non-interacting theory, you get a mixing between these states with the same quantum number. So you cannot really tell the difference between this mesonic state and this glue ball, which is a pseudoscalar glue ball. In the literature, there has been some discussion whether this multiplet should be the lightest or this one here.
Yes.
But it's hard to tell the difference. In fact, when we did what I shown here, what is shown in the final plots is actually a mixture of this one and this operator, which generates the lightest state. And we have also calculated, tried to estimate the mixing in the ground state and first excited state and try to disentangle this. But it's hard to interpret this compared to a continuum where you also would have some mixing between the two multiplets.
I see. Thank you. No, there's supposed to be two states, and then one is heavier than the other one. And that's exactly the point.
Yeah, I mean.
Well, no, but I wanted to see if there was degeneracy on top of the lightest glue ball to the next one. If you have supersymmetry, the glue ball, globalino, on the first one, the second one would also be degenerate with its fermionic partner.
To make a more precise statement, what we observe is actually that the ground state is a mixture of these two operators. And the first excited state and the ground state in the pseudoscalar channel is largely dominated by this operator. We don't completely understand it. We don't know how to translate it in the continuum, but it seems that this glue ball here, so this is a mixture, but this glue ball seems to have more overlap with the first excited state. But so you have still some kind of splitting between these two.
Okay.
But you have to look at the complete operator basis and then make the try to project at the first and excited state to get.
Okay. Thank you. Okay, I'm going to declare that the session, that the questions are done, so we can go to the next talk. Okay, thank you very much. And then the next talk will be Szechuan Cheng.
Yeah, I'm here. Do I share the screen?
Wait, we have to make you co-host and make it work out. Okay, you're co-host now, so you can start sharing your slides.
Okay.
Okay.
Do I start?
Give me a second. We're adjusting the screen. Okay, so The next talk will be Bootstrap, the Lattice Jangles theory by Sasha. So go ahead. You have 30 minutes. I'll call you 5 minutes before the end to give you the 5-minute warning. Okay?
Okay, thanks.
Okay, go.
It's my great honor to present my work, Bootstrap, the Lattice Jangles theory, collaborated with my PhD supervisor, Vladimir Kazakov, who is the real expert in matrix model and integrability and who teach me a lot during this project. This work is a direct follow-up of Anderson and Kruczynski they did in 2017. Martin also gave several lectures on this topic last week. So although I will be as self-contained as much as possible, when it comes to the topic that's already covered by Martin last week, I will be brief. And feel free to stop me at any moment if you have any questions about it. Okay, let's begin. So the Bootstrap method, it is basically solving the problems in theoretical physics by the optimization theory. A simple example of optimization theory is the semi-definite programming, which we will use a lot of times during this project. That is, we minimize linear combination of variables subject to some linear semi-definiteness of a linear matrix. And this kind of semi-definite programming, or SDP, it falls into the class of convex optimization. Generally, we cannot solve a large-scale non-convex optimization problem. It's like solving a linear system of equation or nonlinear system of equations. They are on different level of complexity. Solving convex optimization or non-convex optimization, they are on different level of complexity. So we should keep it in mind because we will see some non-convex things later. Okay, let's start with some a simplest bootstrap model or a toy model or a prototype of all our method in this project. That is, if you like to call it, it is a zero-dimensional phi-4 theory. It is nothing but a quartic integral, an exponential integration over quartic potential. Everyone knows how to solve it both analytically and numerically. But here we are going to use Bootstrap method to solve it. Here, our goal is, or our observable is case moment under this partition function, equation 4. That is x to the k integrated over this quartic integral. For the Bootstrap method, first we notice that there are Schwinger-Dyson equations, which we will get from do an infinitesimal variation by changing x to the x plus epsilon. Or we can get such equation by integration by part. Anyway, it is equation 6, which is a linear recursion relation relates with different moments of the partition function. And we also have the global symmetry, which means that all the old moments, they are 0. This is just because the symmetry of the original partition function. Although this seems naive, you cannot derive the global symmetry just by the recursion relations. They are totally different. So by these two equations, we can actually solve all the higher moments. Of course, the higher even moments, all the moments they vanish. We can solve all the higher even moments as a linear function of W2. Okay. So what else? To solve the W2, we don't have any information from the Schwinger-Dyson equation or the global symmetry. Here we propose to consider the following inequality, that we integrating the measure against the square of any polynomial of x. Then this must be positive. Why? Because you are integrating a positive function against a positive measure. This is definitely positive. But we notice that this must be true for any polynomial. And this polynomial, we can formulate this condition, equation 8, in terms of a quadratic form in terms of vector alpha. So for any alpha, this is true, which means that this is a positive positive semi-definite quadratic form. And the matrix in the middle of the quadratic form, it must be positive semi-definite. So this is equation 9. This is the matrix in terms of all the moments of the partition function. And we notice that the old moment, it vanished. So there is actually a lot of zeros inside. And we notice that the higher moments, they are linear functions of W2. So this infinite dimensional positive semi-definite matrix, it is actually a linear inequality on W2. This condition will be referred to as positivity of the correlation matrix because it is a matrix of correlators. Okay, so how to do the bootstrap? Here, we can make a truncation of that correlation matrix, infinite dimensional, to truncate it to the top lambda plus 1 times lambda plus 1 some matrix of W. And we can minimize or maximize W2. This is a semi-definite programming already. So how it will work? For this simplest model, we have the analytical result for reference here. Everyone can get it by just typing the integration into Mathematica. And if you put g equals 1 and lambda equals 10, we can also get the bootstrap result. So the number on the left-hand side is when we minimize W2 under the inequality. And on the right-hand side, it is maximize W2 on the inequality. So we see that in the middle, this is the exact value. So we get that our bootstrap result, it is actually highly non-trivial. We get already for lambda equals 10, we get 6 digits already. So this the result is highly non-trivial. And for different g, you can see that in the middle, the dashed line is the analytical result. And when you are increasing the lambda, the allowed region for W2, it is shrinking very, very fast. Actually, for lambda equals 5, which I didn't plot here, it is already indistinguishable from the plot. Okay, for this toy model, I have a final remark. As you have noticed, there is a lot of zeros in the correlation matrix. Actually, we can rearrange the indexes of the matrix and put it into a block diagonal form. The first block corresponds to the square of the even moment, and the second block corresponds to the square of the odd moment. Although they look similar, actually they are independent from each other. Why this happened, I can tell you at the moment that this is because even powers of x and odd powers of x, they fall into different representations of Z2 symmetry. You remember that Z2 symmetry is the symmetry of this model. And what I want to indicate here is that if we have more non-trivial global symmetries, then we will have for each irreducible representation of the global symmetry, we will have a independent block for that symmetry. This is what we will discuss for Yang-Mills. Later, I want to show you that this method, this bootstrap method, it is actually a serious numerical method. Look at this model. This is a 2-matrix model in the large N limit. So this is already an integration with infinite number of degree of freedom. And to the best of our knowledge, this 2-matrix model is not solvable. And if we use above method for this model, at lambda equals 11, which means that we are doing the bootstrapping over all the moments in terms of A and B with length less than 22, and with G equals H equals 1, then we have a 6-digit result. Here, the plot is a shrinking of the island of the trace A to the 2 and the trace A to the 4th. Okay, so from some studies, we already get that this precision we got is actually better than the Monte Carlo, actually much better than the Monte Carlo precision we could get for the large N matrix model. Okay, let's go to the main topics of this project. That is large N Yang-Mills model, large N Yang-Mills model on the lattice. here, this is the traditional Wilson action, and we are doing the integration over a 2-dimensional, 3-dimensional, or 4-dimensional space-time lattice. And our goal here is to bootstrap the one plaquette average here. I can show you the result first. Here, the result is 3D and 4D result. And the yellow region, the orange line, and the blue line, they are the rigorous upper bound and the lower bound of the one plaquette average. The dashed line is the perturbation result, both in the weak coupling limit and the strong coupling limit. And the red dot, they are the Monte Carlo result, and also the purple dot. So you see that especially in 4D, which is most interesting, we are, especially in the weak coupling limit, we already get a very, very precise result. So later I will describe how to get such a result. Actually, all the method goes very parallel to the toy model. Let's look at it. For the observable, for the toy model, we are bootstrapping the case moment. And for the lattice Yang-Mills, we are doing the same things for Wilson loops. Actually, expectation of Wilson loops. And for the action, for the toy model, we have quartic action, but for Yang-Mills, we have the Wilson action. The equation of motion, they are both just Schwinger-Dyson equations. For toy model, there are some linear recursion relations. But for the lattice Yang-Mills, it is the so-called Markinko-Migdal loop equations. There are some equations relating different Wilson loops. For the symmetry, the toy model symmetry is Z2, we already described. But for the lattice Yang-Mills, we have the lattice symmetry, plus the C here denotes the charge conjugation symmetry. Actually, it is reversing the Wilson loop. That means Wilson loop, whether it goes one way around or the other way around, they have the same expectation value. For the positivity, for the toy model, it is a Hankel shape matrix. But for the lattice Yang-Mills, actually we have more positivity conditions. One of the positivity conditions is just like the old one, that is by Hermitian conjugation, we get the product. Actually, we have more positivity conditions I will describe. And for the convexity, for toy model, it is a perfect convex optimization problem. But we will see that due to the large n factorization, the loop equations, they are not linear. So this is actually not a convex problem. We need to do some convex relaxation to make it perfect SDP. Okay, let's begin. First, we begin with the Markinko-Migdal loop equation. Martin has already described this subject last week, so I will be very brief here. Here is a loop variation corresponding to the link we are doing the variation. Here I just give you several simplest examples in 2-dimensional lattice, how the loop equation will look like. This is when we are doing the variation on a link of the single plaquette, we will get such a loop equation. And we also have the backtrack loop equation. We see that if we put a backtrack on the margin of the one plaquette and doing the variation on this link, although without variation, this new Wilson loop, it is exactly identical to the one plaquette due to the unitarity. But when doing the variation, they are different. It gives non-trivial loop equations. The backtrack can be infinitely long, actually. So you can imagine there is very long backtracks starting from a non-trivial Wilson loop. Okay, this Wilson loop, the figure 8, it looks like number 8. This is the one of the lowest order nonlinear loop equations. So the nonlinear terms, it only appear when we have overlapping links. Okay, this finished our very brief introduction to the loop equations. For the positivity conditions, suppose we must take some, let's say, several Wilson paths starting from the same point and end at the same point. Here, for the simplest example, we get the it starts from 0, 0 point and end at 1, 1 point. And we use very similar method to the toy model, and we can get such a positivity matrix. This positivity matrix is quite trivial. If you try to solve it, it just means that the absolute value of UP it is less than 1. Of course, this is trivial, but let's say a non-trivial case that in the 2-dimensional case, we consider all the Wilson paths coming from 0 and end at 0, but with a length cut of 4. So this is a Wilson, this is a positivity matrix correspond to it. The 1 here, it corresponds to the length 0 Wilson path starting from 0 and end at 0. And for the other indexes, there are different paths coming from 0 and end at 0 with length 4. So this is a 9 times 9 positivity matrix. And actually it gives us non-trivial bound. We will see. For this matrix, there are all in 6 Wilson loops inside the matrix. And these 6 variables, they are related by 2 loop equations, which we already wrote down. This is the 2 loop equations. And then this is a well-defined SDP. We can do the optimization. And we can, after putting lambda equals 1, for example, you can put lambda any other value, that doesn't matter. If we put lambda equals 1 at this lowest order bootstrap, we will get the 1 placket average larger than 0 and smaller than 0.693. Okay, but if we aim for higher order bootstrap problem, the complexity goes up exponentially. So we must come up with some ideas how to simplify this scheme. One of the complications is that for higher order loop equations, they are nonlinear. And also the matrix, it grows exponentially. And we may have more positivity conditions due to our problem is already much more involved. It's not surprising we have more positivity conditions. Here is the new positivity conditions. It is the reflection positivity, actually. We can not only get a guaranteed positive quantity by taking the Hermitian conjugation, but we can also get the positivity, guaranteed positive Wilson loop by the space-time reflection showed by these 3 figures. So there are actually 3 times of such reflection positivity: reflection by link, reflection by the side, and reflection by the diagonal. So if you take linear combinations, you can imagine that there are 3 more positivity matrices here. And this kind of new positivity conditions, they are actually independent from the old one. Look at the gray curve and the orange curve here. The gray curve is the bootstrap without reflection positivity. And the orange curve, they are the bootstrap with the reflection positivity. Apparently, they are at the same order. They are Lmax equals 12, which means that we are doing the bootstrap with all the Wilson loops with length less than 12. So it is obviously that they are independent. Okay, let's look at the lattice symmetry reduction. Already from the very similar topic, conformal bootstrap and S-matrix bootstrap, we know that the positivity condition, they are arranged to different spin channels. So it is not really surprising that on the lattice, our positivity conditions, they are arranged in different irreducible representations of the global symmetry or the lattice symmetry. This is a lattice symmetry group for different kind of different dimensions. I must notice you that for the reflection positivity, we have less symmetry because the reflection plane, it damaged some part of the global symmetry. So we are, for the reflection matrix, we are doing the symmetry reduction with respect to the subgroup which stabilize the reflection plane. This is detail, just detail. Let's look at this matrix again and see how the symmetry reduction works here. So we can take linear combinations of different Wilson lines and to put them into different representations of two-dimensional point group of the lattice. And we take the inner product here to get the inequality condition. The linear combination fall into the different irreducible representation. They are, by the group theoretical construction, they are orthogonal to each other. So we get block for each irreducible representations here. So this series of very simple equality, this is actually exactly equivalent to the old 9 times 9 positivity condition. So this greatly simplifies the problem. And also the relaxation. I don't want to spend too much time because the time is, I'm already running out of time. Let's look at suppose we have a single quadratic term in the loop equation, and we introduce a new variable, let's call it T1 in the place of the quadratic term. So we note that x squared equals T1. This is a non-convex condition. Why? Because all the nonlinear inequality, they are generally non-convex. But we notice that x squared smaller than T1, smaller or equal than T1, this is convex. Why? Because we can rewrite them in terms of semi-indefinite matrix form. This is definitely convex. So by this, what we have done, we have forget T1 is a square of x, but this new variable T1 is subject to a positive semi-indefinite matrix. This could be generalized to a vector case. That means here the x is a column vector. Suppose the x is a column vector of the Wilson loop, and we introduce a new variable or new matrix in the place of the quadratic terms in the loop equations. And then we forget they are the quadratic terms of the Wilson loop, but they subject to the new relaxation matrix positivity condition, that is equation 34. So we introduce some new variable, and this subject to the new positivity conditions to make the whole system convex. This is how the relaxation works. For example, for our Yang-Mills bootstrap at Lmax equals 12, our correlation matrix, our relaxation matrix is this 2 times 2 matrix. Here, the Q is a variable in the place of square of 1 placket average. Okay, then we finish. This is our final scheme. We minimize or maximize the 1 placket average to get the rigorous upper bound and lower bound. This is subject to the condition of Marcinko-Migdal loop equation, and also the correlation matrix factorized with irreducible representations of the global symmetry, and also 3 kinds of reflection positivity matrix also factorized with respect to the irreducible representation, and finally the relaxation matrix. This concludes our construction of the scheme. Okay, this is the result of our bootstrap. For 2D, I notice you that the large N Yang-Mills on 2D dimensional, this is exactly solvable. And the UP here, the equation 37 is the exact solution of UP. And here, this is in the plot, this is our bootstrap result. The yellow, orange, and the blue line, they are the shrinking allowed region when we are increasing the bootstrap cutoff. Actually, this is instant. This doesn't take any time to finish this plot. But for 3D and 4D, the complexity grows exponentially. So if this takes, let me say, for 4D, for each single point on the plot, it takes approximately 20 hours to finish it, 20 hours CPU time. Okay, so let's look at the final plot. For 4D, as I already said, in the weak coupling phase, our bootstrap upper bound is very close to the Monte Carlo result. Actually, in the weak coupling limit, it is already better than the Monte Carlo result. And it goes very close to the perturbation line. This is a third order perturbation line. Okay. Yeah, for the I also must notice you that for the weak coupling phase, this is a physically important phase. For the strong coupling phase, it doesn't flow to the continuous QCD when n equals 3. So this is less important here, actually. Okay, we are close to finish. This is some future directions which I want to mention. And this is actually the ongoing directions. The first 2 points, I think it will, we will get some results very soon. The first one is technically our algorithm, still it is much perfectible. For example, the positivity condition, that means that the positivity matrix, it is unlikely that the whole positivity matrix, it contains all the part of it is equally important. This is very likely that a very small part of the positivity condition, it already contains 99% of the information. So we need to come up with a very clever way to select the positivity condition. When this is done, we can easily push the bootstrap cutoff to Lmax equals 24. At this cutoff, we expect that we will have precision very close to the Monte Carlo maybe. The second point is our scheme. This is not at all limited to large N, as you can see from the toy model. This is actually, as long as you have a positive measure, this will work. So we can expect that we can directly bootstrap matrix model like in n equals 2 and n equals 3, which means SU2 matrix model, SU3 matrix model, or SU2 and SU3 lattice Yang-Mills theory. And the third one, here, unlike Monte Carlo, it has some finite space or finite volume finite volume uncertainty or statistical uncertainty. All our bounds, they are rigorous. But if we don't insist on such rigorous margin, we expect that we should get more precise result. Actually, this demands us on a new effective action to minimize. We are not anymore minimizing the plaquette average, minimizing or maximizing the plaquette average, but we need to figure out some new effective action to minimize. If this is done, then we have more precision even at Lmax equals 16. Okay, I'm finished. Any question?
Thank you.
I have one question.
Yes.
So I'm wondering whether anybody has supersymmetrized the loop equations.
Yes. I think Martin tried it, but I didn't follow that part of his work. If you can ask Martin directly how this works, but it seems generalizing this story to the supersymmetric Yang-Mills theory, this is not trivial. It seems not.
It doesn't have to be supersymmetric Yang-Mills. It could be some simple supersymmetric model. For example, you showed these quartic models. One can supersymmetrize that.
Yes, then of course, I think it will work. There is actually someone tried to someone tried to bootstrap the fermionic system already. You can follow such work. So fermionic there is no problem. So I don't think there will be any problem with supersymmetric things.
Okay, thanks.
Yes.
Masanori.
Yeah. Is it possible to avoid sign problem in this approach?
Yeah, this is a very good question. This is an open question because till now we didn't seriously tried models with sign problem. The Hermitian conjugation for sign for the models with sign problem, it may be problematic, but the reflection positivity, it seems it still holds even if there is a sign problem. So this is possible that this method, after some modification, it still works. Yeah, this is open till now.
Yeah, I asked in many supersymmetric theories, we do sine quench, phase quench simulation, and somehow it's working. But if you can somehow justify it, it could be fun. So
yeah, this is a very, very
good
infrastructure direction. I agree.
I have a question
Yes?
about this going to the continuum limit. The single plaquette is, I think, I mean, it's at the cutoff, right?
Yes, it's a UV quantity actually.
So I would think to get the information you want that is universal rather than specific to the action, you would want to probe something at a correlation length which represents continuum physics. Is that what you're saying that you would try to do?
I mean, we are bootstrapping the single plaquette, which is the UV quantity. But at the same time, you can bootstrap.
Right, but I can change the action. I can change the action almost arbitrarily at that scale.
Yes.
And I would have the same continuum physics.
Yes.
Exactly the same, right?
Yes.
So,
but the loop equation, it will be more involved if you choose some more involved action other than the Wilson action.
Right.
And even in this scheme for the Wilson action.
Maybe I should look at these curves a little bit carefully. So where's the continuum direct? Where's the smooth part in these curves?
Let me.
So weak coupling is which way? It's lambda.
It's a lambda to 0. But when you go to the lambda to 0 to get the meaningful physics quantity, you will need very large Wilson loops to get it. This is computationally demanding.
I mean, maybe, I think you mentioned, maybe if you did something like a Wilson flow lattice, can you do it for that? I mean, the point is that eventually you want to set a scale, right?
Yes.
And you don't want to, and you want to be infinitely far from this cutoff plaquette.
Yes, our current framework, we are just trying to make the bootstrap cutoff larger and larger, so we will get to access to very big Wilson actions. But I think there will be better solutions.
But then you will have to actually look at Wilson loops that are larger?
Yes. We can directly, for example, you try to maximize the single plaquette, right?
Yes.
By this way, you not only get the single plaquette value, you get the whole spectrum of all the Wilson, all the Wilson actions below the bootstrap cutoff. All the Wilson loops below the bootstrap cutoff.
If you had the full solution of the Migdal-Makenko equations, then you'd get everything, right?
Yes, but we have a solution with a length cutoff.
But you have an iteration which takes you from the single plaquette up a few lattice spacings, right?
Yes.
And I could then introduce another action, which would be exactly the same at the physical universal place, right?
Yes.
It would totally change these equations.
Yes.
So doesn't that mean you have to somehow go to, very large order of these constraints?
In principle, in this framework, yes. Yes, you need to consider very large bootstrap cutoff. But it is not length Lmax equals 16. This is equivalent to which volume size? I think it's 30, somehow like 32 to the 4 in the Monte Carlo simulation, the space-time volume. So this is already not very small.
That's a finite volume effect. I'm worried about the cutoff effect.
Yes.
Anyway, well, it's very interesting, but I have to understand it better. Thanks.
Yeah, but I want also to mention that most of the positivity conditions or the loop conditions, actually they are correct for large enough lattice spacing volume, a lattice volume. So this is actually, this is in some sense, approximately, this is a uniform bound for big enough lattice. You can understand it this way. Not necessarily infinite volume, but of course infinite volume and large enough lattice. Yes.
Okay.
Okay. I'm going to cut the discussion there. Thank you, Szechuan.
Okay. Thanks.
Okay. I think we have a break of 15 minutes. Szechuan, before you leave, I have a question.
Yes, I'm still
Yes.
here.
Do you need to use arbitrary precision in your Bootstrap calculations?
Not at all. The solver I'm using is Mosaic. It is machine precision. It is very surprising that in this case, we don't really need arbitrary precision, unlike conformal bootstrap or S-matrix bootstrap.
Well, I think that that's related to the fact that the Wilson loops are of a unitary matrix and they're bounded above. So that should be something that kind of makes the matrices a little bit better behaved, right? Because the coefficients are of order 1, not of n factorial.
Yeah, in some sense, yes. But for the two matrix model I discussed in the middle, I also used a machine precision after some careful normalization of the matrix.
But there you use factorization. It's in factorization that this problem disappears. As soon as you remove factorization, when we study quantum mechanical systems, things grow like factorial in the moment. And this seems to be a numerical issue that I'm trying to understand.
I'm not very sure about it. I'm also doing some bootstrapping on the quantum system. For the current, I didn't see any problem with precision. So most of the time, I think after some normalization of the SDP to make it
one has to normalize it too. Yes.
Yes.
Okay.
Yes. It seems machine precision is enough. It seems. Although I'm not, I didn't fully understand this problem.
Okay. Thank you.
Mm-hmm.
Take care.
Okay.